Hello, my name's Lloyd Tinkler. I work at the University of Sheffield Advanced Manufacturing Research Centre. In this talk, I'll be presenting the foundational work we've been conducting over the last year towards Grand Challenge 2.3 of the Future Electrical Machines Manufacturing Hub. And this is on the enabling technologies for flexible and customised manufacture of high-value electrical machines. When we think of manufacturing, we might frequently think of highly automated factories which turn out near identical items at very high speed. However, this mass production just defines one end of a spectrum that can be roughly broken down in terms of the production volumes and number of variants, which is shown here graphically. In terms of electrical machines manufacture, we see mass production of motors that go into consumer electronics, white goods, more recently in automotive for electric vehicles. So this defines a region shown top left here with high production volumes but relatively low number of variants. Thanks to the economies of scale in the use of automation, these mass-produced items can be manufactured at reasonable quality, and importantly at low cost. Conversely, for highly specialised electrical machines where the performance and integrity are paramount, the high cost means that production volumes are typically quite low. This means that any manufacturer might see a large degree of variation, which makes automation unsuitable. This necessitates highly skilled, labour-intensive bespoke manufacture which drive the cost up further still. Recently we have seen a drive for flexibility in mass production, and this has been facilitated by greater intelligence within the manufacturing systems themselves. This allows them to accommodate a greater degree of variation, and it's exemplified in the automotive sector where a car can be customised to the client specifications at each stage of the manufacture. For example, the engine size, interior trim, the wheels can be chosen to produce a car which is unique to the customer. However, this flexibility is limited to the options baked in at the outset. For example, one could not ask for a trim from a different model no more than we could ask for a motorbike or a washing machine. For our manufacture of high-value electrical machines destined for some high-integrity application, we cannot know in advance what sort of machines we might need to manufacture. We might know the common elements, for example the state of the rotor, the coils, the casing, and common processes such as cutting of sheet steel laminations, consolidating the stack, coil winding, and so on. So in this grand challenge we seek to develop a middle ground which brings the benefits of mass production, of automation in particular, and the associated improvements in process reliability to low volume manufacture of high value machines. Having this flexibility could bring the benefits of mass production and automation, such as greater throughput efficiency, process reliability, and give manufacturers a competitive edge by shortening the route to market. Moreover, this would shorten the route to exploitation of research from the UK's leading academic community in PEMD, again offering a competitive edge to manufacturers. Together this could ensure the resilience of UK manufacturers by allowing greater diversification of product mix, and even the remanufacture and repair of existing products. In short, the challenge here is to make our manufacturing systems and automation intelligent enough to cope with greater product variation. Grand Challenge 2.3 will address this across three areas. Firstly, a structured assessment of the opportunities for flexibility. This will be a paper-based exercise which will investigate the commonalities between machines and the manufacturing processes, and in trends of manufacturing research, in particular agile manufacture. Secondly, we will investigate the use of remote laser cutting as one of these enabling technologies for flexibility, with the aim of providing an alternative to stamping or conventional fusion laser cutting. Through this flexibility offered by remote laser cutting, we will investigate the design possibilities opened up by tailoring each of the layers of the laminated core to produce a pseudo three-dimensional structure. Of course, laser cutting can already be used in this way, however the slow speed when compared to stamping make it an unattractive option for high volume production. Therefore it seems that designers are bound by the practicality to keep the structure uniform throughout the stack. Additionally, complex shapes and thin layers tend to result in greater thermal damage. Consequently, the design and the performance of the resulting machine is compromised by considerations of the manufacturing process. Importantly, remote laser cutting has been shown to offer a speed up factor of perhaps 5 or so, whilst inducing less thermal damage. Therefore, with development, it might offer a viable alternative to stamping, and thus make these pseudo three-dimensional structures a viable option to designers. Finally, we'll be investigating how digital twins of these flexible manufacturing processes could be used to support the flexibility and customisation of the factory as a whole. For instance, if from simulation we can estimate the process time to cut a laminated core and the corresponding thermal damage, we might be able to better plan the throughput through our factory and optimise the design. Additionally, this challenge has a link to Grand Challenge 2.2, through which we'll be developing the robotic coil winding cell as the basis of one of these flexible manufacturing systems. So over the last year, the majority of our efforts has been on these two activities, and this is really laying the foundations for the research to come. I will now hand over to my colleague who will give you an introduction to the work we've been doing on robotic coil winding.
Welcome to the second part of this presentation on the FEMM Hub Grand Challenge 2.3. I'm Gianmarco Pisanelli, Control and Systems Engineer at the AMRC in Sheffield. I'm currently working on the construction of a robotic coil winding cell for the flexible manufacturing of high-end electrical machines. In this short presentation, I will cover a brief summary of coil winding to introduce you to the standards currently applied in industries to produce winding of electric motors and generators. Then I will briefly touch on the importance of tension on winding quality, followed by an outline of general aim of the robotics winding cell. Finally, I'm going to talk about the needle winding end effector that we have designed, a hardware-in-the-loop simulation that we're developing, and the future steps for the robotic coil winding cell. Two basic concepts that I need to introduce before explaining the aim of the project are the difference between distributed and concentrated winding and the importance of an orthocyclic winding scheme. Generally, a distinction is made between distributed and concentrated windings. If only a single coil is wound around a bobbin or a tooth, it is referred as concentrated winding. If the coil spread over multiple teeth, it is referred to as distributed winding. There are multiple ways of arranging the coil tongues, and these are referred to as winding schemes. The orthocyclic winding scheme consists of a special layer structure in which the windings of the upper layer are in the grooves provided by the lower layers. This is the scheme that can achieve the maximum copper fill factor, which is a measure of how much copper wire is inserted in a single slot. Given that the magnetomotive force is proportional to the number of turns and current in the windings, the higher the fill factor, the higher power density can be achieved. Orthocyclic winding schemes can only be achieved by direct winding processes, where the winding is manufactured at its place of function rather than being separately mounted on a further bobbin. There are only two types of direct winding processes for internally grooved stators. One of these is the linear winding. In the linear winding method, a winding is produced by winding the wire into a rotating coil body. The guide tube then moves left to right to form the turns and then back if more layers are required. It is generally preferred in lower value, high volume applications due to its simplicity and fast production rate. However, it is quite limited as it does not offer the possibility to wind coils in a distributed fashion. Another winding technique that allows to achieve orthocyclic winding is the needle winding technique. It is generally used for concentrated winding, but in recent years, the needle winding technology has presented itself as an alternative to an insertion technique, also called trickle winding, for the production of distributed windings of fully laminated stators. In needle winding processes, the Y guide, which acts like a needle, directly navigates along the placement contour around the bobbin. The nozzles or needles are adapted to the part which is to be wrapped. Although considerably slower if compared to linear winding, needle winding can perform concentrated and distributed winding, therefore granting higher flexibility than any other winding process. One disadvantage of needle winding is that it could cause higher stresses on the wire. I briefly mentioned the trickle winding technique in the previous slide. This is the industrial standard for the manufacture of fully laminated stators. The trickle winding is the oldest winding process. Today, it is mainly used for manual repair of electrical machines, as well as in manufacturing of high-performance machines. The trickle winding is characterized by the highest winding quality for electric motors, as the position of every individual wire in the groove is manually adjusted and optimized, usually by means of auxiliary tools like the wedge shown in the picture. Although very old, trickle winding is the most complex method to automate. The tensile force of the wire during the process has a crucial influence on the productivity and product quality. An excessive wire tension can result in a higher coil resistance, damaged wire insulation, a bobby deformation or deviation from the desired coil geometry, and in extreme cases, wire tearing. A low wire tension usually leads to loose wire ends in the windings or errors in the layer structure due to uncontrolled residual wire stresses. For applications in winding technology, the yield limit is relevant as a process limit. It should not be exceeded, since aside from a permanent reduction of the wire gauge, strain hardening sets in. Both have negative influences on the electrical resistance. So now that we all have a basic understanding of the key concepts of coil winding, I can discuss the aim of the robotic coil winding project. We aim to use 2 robotic manipulators to perform coil winding with the aim of supporting flexible production of high-value electrical machines. A bespoke end effector is due to be manufactured in-house and then mounted on one of the robots to perform needle winding. Later, the linked kinematics capability of the 2 robotic arms will be explored to attempt trickle winding to wind high-end electrical machines. The needle winding end effector that we engineered is designed to wire a wide range of copper wire sizes, specifically 0.4 to 1.5 mm in diameter. It has a modular design to accommodate different bending rated requirements. It is capable of measuring the tension and adjust it through the use of a servo tensioner that is also mounted onto the robot. And finally, its head is designed to move to plus and minus 90 degrees to allow upper and lower routing, concepts that clearly explain in the GIFs below that I borrow from the Marsili website. In this slide, you can see a few pictures of different views of our needle winding end effector that we are currently manufacturing. Finally, I wanted to touch on a simulation package that we are using to create a realistic and accurate simulation of the needle winding process. This is created through SimScape Multibody, a package provided in Simulink that provides a low-level physics library that can be used to simulate rigid bodies with linked kinematics, simulate control algorithms before deployment to real hardware, as well as for fault detection. The reason why we opted for SimScape Multibody is that it's the only software with decent off-the-shelf cable dynamics that we could find. It can also exploit the computational power of MATLAB and Simulink. And finally, it offers direct connection to a TwinCAD PLC for a seamless hardware-in-the-loop experience. To conclude this presentation, the future steps of the robotic coil windings are the following. We are currently designing the control cabinet to manage the different components of the cell in a safe manner. We are also designing a tensioner that will allow the wire to be placed inside the stator at a constant tension. We will constantly improve the simulation that I described in my previous slide to be as realistic as possible. And finally, we will start winding in the next month and publish our results by the end of the year 2021. Thank you.
In this final section, I'll be introducing remote laser cutting and describing the work that we've been doing in developing a cell to conduct this research. So remote laser cutting is a technique which has been developed over the last decade or so, facilitated by the advent of high brilliance lasers. In conventional laser cutting, the laser is directed down onto the workpiece. The molten material is pushed through the cut, known as a kerf, by an inert shield gas, which also serves to cool the workpiece. However, for very thin sheets, which would be advantageous in electrical machines, the lower thermal and physical mass of the part can lead to thermal damage at the edges, as well as the parts lifting up due to the pressure of the shield gas. In remote laser cutting, we rely on the pressure of the vaporized material to push the material out of the cut, progressively removing tens of microns at a time by scanning the beam over the workpiece. This requires power densities on the order of tens of megawatts per centimetre squared. The high-speed scanning is often facilitated using a galvanometer with a lens some distance away, hence the term remote. Due to the low inertia of the mirrors inside the galvanometer steering the beam, this can operate at much higher surface speeds than a conventional laser cutter with its heavy linear axes, particularly over complex geometries such as stator teeth, which require the laser to abruptly change direction. So the Fraunhofer IWS in Dresden Germany has been particularly active in this field, and they've demonstrated cutting speeds using this technique of over 100 metres per minute. For comparison, a conventional laser machine might achieve tens of metres per minute. So we could be several times faster when cutting these thin sheets. However, from the graph on the right we can see that up to around a millimetre we might see no benefit whatsoever. Moreover, above a certain thickness there isn't sufficient vapour pressure to push the ejected material out of the kerf, so the process effectively stalls. One caveat to note is the size of the parts. From the figure on the right we can see this is for a 100mm diameter circle. One strategy to increase this field of view could be to increase the focal length of the optic, moving the galvanometer back, much like stepping back to get everyone in a group photo. This would have the benefit of increasing the surface speed, but would be at the expense of resolution in the movement. As we increase the focal length, the field of view increases linearly as shown in the graph. However, the diameter of the spot on the workpiece also increases linearly. Consequently, the amount of optical power per unit area drops off according to an inverse square law. Therefore, to increase the field of view whilst maintaining a sufficient power density, we would also need to increase the laser power. Unfortunately, then we come across a practical consideration of cost, which doesn't necessarily increase linearly with the amount of laser power. To overcome this challenge of the limited field of view, we could cut a section, move the workpiece and then cut another, and stitch multiple areas together to cut the entire part. Arguably, however, this start-stop movement doesn't maximise the potential of the stages moving the workpiece, and it means that there's a waiting time between processing each area as we tile across the part. As such, a few companies have developed a means of synchronising the movement of the galvanometer to some stages. This allows simultaneous movement such that we can prioritise large movements, for instance tracing the outside of the stator to the stages, whilst the galvanometer fills in the fine detail such as the stator teeth. And this is the approach that we've taken on the system that we're developing. So in our system we're coupling a 2 kW fibre laser to a galvanometer. This galvanometer is synchronised to two 600mm travel linear stages to extend the working volume. And then finally we're integrating a robot to allow for automated tending to load in the sheets automatically and pick out the cut parts. Through trials with a laser supplier we've found is results consistent with that in the literature of sort of several hundred millimetres per second. So in summary, the last year has pretty much been laying the foundations of the future research that we do in developing a robotic coil winding cell focused particularly on needle winding and development of a remote laser cutter. We anticipate that both of these systems will come to fruition about February-March time of 2021, with results following shortly after. Thank you for your time, and please do keep in touch.